All right, welcome to this Masterclass Explainer. If you're a graduate electrical engineer gearing up for the high-stakes offshore industry, you are in exactly the right place. Today, we're zooming in on the absolute heart of offshore power, gas turbine-driven generators. Okay, let's dive right into this.
Picture this. You're standing on the steel deck of an FPSO platform out in the Gulf of Mexico. It's 2 a.m. The air, a sweltering 35 degrees Celsius, and the humidity is sitting at a totally suffocating 100%. But even in the dead of night, you can feel this deep, visceral vibration just humming right through the soles of your boots. You know, that vibration? That's literally the heartbeat of the entire offshore power system.
And you know what's causing that hum? It's the machine directly beneath you. A gas turbine, just spinning relentlessly at 3,000 RPM. It's continuously burning raw wellhead gas to produce, well, every single watt of electricity that's keeping that platform alive. As an oil and gas electrical engineer, this machine is your ultimate responsibility. So understanding exactly how it turns raw gas into life-saving power, yeah, that's simply not optional.
Section 1. Anatomy, the Joule-Brayton cycle.
So, to master the physical reality of this beast out on the rig, we really need to grasp the theoretical physics driving it. If we strip away all that heavy steel casing, what we actually have is a heat engine, and it operates on the simple cycle version of the thermodynamic Joule cycle, or, as you might hear it called, the Brayton cycle. It all happens in 3 elegantly simple continuous stages. First up, we compress. We take incoming ambient air and squeeze it to a super high pressure. Second, we combust. We mix that high-pressure air with fuel and ignite it right there in the chamber. And third, we expand. Those resulting hot, incredibly high-velocity gases shoot out and expand through the turbine section. And that rapid expansion, that is exactly what creates the immense rotational power on the shaft.
Now, when we break down the math here, it's actually surprisingly elegant. If we look at the formula for the total work done by the turbine, which we denote as UT, it's just the specific heat capacity at constant pressure, that's our CP, multiplied by T3 minus T4. Okay, so what does that actually mean for us in the real world? Well, T3 is the scorching hot temperature of the gas as it enters the turbine, and T4 is the cooler temperature of the exhaust when it leaves. Basically, the physical temperature drop across that turbine is directly proportional to your actual mechanical work output. In short, you extract heat, you get power. It's really that simple.
But you know, here's the catch. Not all of that massive power goes straight to your electrical generator. Look at how this energy divides up. Roughly 55%, and honestly sometimes up to 60% of the gross energy output from the turbine goes right back into driving its very own air compressor. It takes a monumental amount of energy just to keep the thermodynamic cycle breathing. So that leaves only about 45% as your net shaft output. That smaller, remaining slice of the pie right there, that's what you actually have available to spin your generator and power the platform. Kind of wild when you think about it, right?
Moving on to Section 2. Choosing the right turbine.
Now, what's really interesting about this is how the environment dictates the hardware. I mean, oil and gas environments range from floating ships in the middle of the ocean to massive, sprawling refineries out in the desert, so one size absolutely does not fit all. Engineers have to select specific hardware for drastically different realities, and there's a stark contrast between our 2 main categories of field turbines. On one hand, we've got aeroderivative gas turbines. These are basically modified aircraft jet engines. They boast an incredibly high power-to-weight ratio, plus they feature modular, super easy maintenance. You can literally swap out a core engine block quickly, which makes them absolutely ideal for weight-critical offshore platforms. On the other hand, we have heavy industrial gas turbines. Now, these have a pretty poor power-to-weight ratio, and they take up a massive physical footprint, but their superpower? They offer incredibly long, reliable running times between major overhauls, and they can burn much dirtier fuels. So you're going to find these massive machines anchoring large, fixed land-based facilities like your typical refineries.
All right, Section 3. ISO ratings versus reality.
So when you go out and purchase a multi-million-dollar turbine, the manufacturer is going to guarantee a specific power rating. But let me tell you, there is a very sharp contrast between the pristine textbook conditions of that rating and the harsh, dirty reality of the actual oil field. To establish their baseline rating, manufacturers test these machines under strict ISO reference conditions. What does that mean? It means an ambient air temperature of exactly 15 degrees Celsius, an altitude right at sea level, and a very comfortable 60% relative humidity. Basically, it's a perfectly cool, and honestly somewhat unrealistic spring day.
But wait. Think back to our scenario from the very beginning of this explainer. You're offshore in the Gulf of Mexico, and it is 35 degrees Celsius. So as the engineer in charge, what exactly happens to your power generation when the ambient temperature spikes so far above that 15-degree ISO baseline? Remember your basic physics here. Hot air is less dense, and that means less oxygen is physically being pulled into your compressor every single cycle.
So the crucial point is this punishing reality. For every single degree Celsius the ambient temperature rises above that 15-degree ISO reference, your gas turbine suffers a continuous power derating penalty of 0.5 to 0.8%. Let's put that into perspective. If you're operating at 35 degrees, well, you're 20 degrees over the limit. That means you are instantly losing anywhere from 10 to over 15% of your total generating capacity simply because of the weather. No mechanical failure, just a hot day. You absolutely have to actively account for this reality when you're managing the offshore power grid.
Section 4. Action. Droop governing under load.
Up to now, we've mostly talked about static conditions, right? But an offshore power grid is highly dynamic. Let's see how this builds during a major transient load event on the platform, and how the turbine control systems actually keep the lights on for us. Step 1. A massive gas compressor motor suddenly starts across the line. This huge, sudden demand for power physically pulls energy directly from the generator, slowing its rotation down. So in Step 2, as a direct result, the entire system frequency drops below our nominal 50 Hz. The rig's lights might even actually flicker for a second. But instantly, Step 3 kicks in. The turbine's closed-loop speed governor detects this speed error and rapidly amplifies the signal. Moving to Step 4, the governor commands the fuel valve to open wider, injecting a surge of gas into the combustion chamber to compensate for the lag. And finally, in Step 5, that increased thermal energy spins the turbine right back up, and the system frequency beautifully recovers and stabilizes. And the craziest part? All of this incredible orchestration happens in a matter of mere seconds.
Which brings us to our final thought. You now understand the immense physical forces at play within the Joule cycle, the relentless environmental derating penalties your equipment faces just from the weather, and those hyper-dynamic governor control systems that are constantly racing to maintain equilibrium. So, when you finally step off that helicopter and take the helm offshore, how will you manage these razor-thin operational tolerances under pressure? Because make no mistake, the platform's heartbeat is entirely in your hands. Thank you for joining me in this explainer, and keep learning out there.